Obviously, things are a little different this year with quarantine coronavirus. We've had to adapt. Much of this year's STEP conference was online and remote. The portion for the STEPCon High School, we had over 1,400 students and over 20 educators from around California be involved this year, which is fantastic. The challenge is during the award ceremony, there are some educators and students who have class, who are at lunch or have other demands. And so we're recording this session so that we can share with those educators and those students who participated in these modules, so that have a chance to hear from our keynote speakers and from our module leaders. So we do expect we'll see more folks come in as we get a little past 12. But I want to just cover really quick Zoom etiquette. Hopefully over the last 7 months, you've had a chance to be on a Zoom meeting. Please keep your audio muted unless you are speaking or you have something you'd like to share to ensure that background noise does not interfere. If you'd like, you're welcome to have your video on. We encourage that so that our speakers will have some lovely faces and folks to look at. And again, I mentioned that we are recording this session and we're going to share this recording with the educators and the students who participated in the STEP conference, high school. So to kick things off, today we come together and recognize the significant role that science, technology, engineering, and mathematics, or STEM, have in our lives and in our communities. In fact, thanks to many of the people here with us today, and many others, we are able to host today's award ceremony safely and responsibly. Today, we will hear from two keynote speakers, Nobel laureate, Dr. Barish, and Google software engineer, Dr. Damien Octeau. We will also hear from Dr. Matt Barth from our Smart Cities and Transportation module, Dr. Basak Guler from our Artificial Intelligence and Security module, Dr. Sadrul Ula from our Microgrids module, and Nicole Cleary from our Clean Air Sensors module. We will recognize our winners of the awards at the end of this ceremony. But first, I am pleased to introduce Mr. Gordon Bourns. Gordon is the president and CEO of Bourns Incorporated, a global technology and engineering company headquartered right here in Riverside. Gordon has many passions. Perhaps the greatest is his hope of inspiring future generations to pick up the mantle of engineering and science and build a brighter and better future for all of us. To share more about the STEP conference, please join me in welcoming Mr. Gordon Bourns. Oh, Gordon, muted.
Okay, thank you. Thank you, Mr. Emmer. I want to begin by thanking the Science and Technology Education Partnership, or called STEP Board of Directors, and the STEP Planning Committees, Yami Shimojo and Greg Nicholas from Riverside County Office of Education, Carlos Gonzalez, who's in charge of MESA for the Bourns College of Engineering at UC Riverside, and Mr. Kim Terry from the San Bernardino County Superintendent of Schools Office in charge of STEM for San Bernardino. And between Yami Shimojo and Mr. Kim Terry, they really head up STEM for our two counties, which covers several million students, it's really a great guiding star to have both of them help us with our programming. Of course, as Mr. Emmer said, we've had a challenge in taking our STEPCon 20 program online. It's created a lot of extra work, but we've learned a tremendous amount. And I want to start, first of all, by talking briefly about the three online, what we call STEM Summer Learning Labs that we held this last July. And in fact, I hope some of our students in our CSERT high school program were also in our STEM Summer Learning Labs, which first was STEM in Public Utilities Learning Lab, or STEM POL, that was hosted with the help of Sharon Gutierrez and Damaris Valles with Riverside Public Utilities. And then we had STEM Solutions, and this was all about how we could improve our safety and also quality of life during COVID-19. In fact, we had the tremendous support of our mayor, police chief, fire chief, educators, even sports people, and people in our public works talking about the challenges of operating and keeping our community going during COVID-19. And finally, our last program was STEM in advanced manufacturing, where we toured 6 different manufacturing companies. Garner Holt Productions featured in today's news press enterprise, in fact, for their learning labs. And they were a tremendous support in our STEM and advanced manufacturing. In each of the programs, we had between 60 to 75 high school students. They participated at no cost to them, but thanks to our many sponsors, they provided the funds necessary to have a combination of online programming and kits that all of the students picked up at Bourns and at CBU prior to each of the programs. We do this because we want to make sure that students are exposed to the many STEM career opportunities that they have in our community, and in fact also to the STEM educations at UC Riverside and Cal Baptist, and our partner too is La Sierra University, all of whom participated in our summer programs. And then this last week was STEPCon 20, a fantastic success, beginning first of all with the educator program. And this is where Dr. Carlos Gonzalez helped us. We had about 250 educators on October 7th, Wednesday, and that was followed by the student conference, which included the high school program, and that was on Thursday and Friday, October 8th and 9th. For me, the highlight was being able to broadcast live from this country's largest magnetic confinement fusion research laboratory at General Atomics down in San Diego. And we had our scientists who run that fusion research facility help us by putting on a science show that showed the different key features of what it takes to have magnetic confinement fusion take place. They talked about the different states of matter, including plasma, and then showed magnetic fields and high energy pulses, and culminating with a detailed description by one of their student scientists of how this fusion generator works. And we hope that that's going to be the long-term source of energy, very clean and limitless source of energy, because that's what powers our sun. So we had over 12,000 students and their teachers attend these 3 days of online programming. In fact, I will post in the chat the link to see this program, because it's all recorded and available up through December 4th. So you can go in and see the full depth of this online STEM education program, including this CSERT program. So now I'm honored to introduce Nobel laureate, Dr. Barry Barish. Dr. Barish grew up in Los Angeles and attended UC Berkeley, where he received his PhD in physics in 1962, specifically in experimental high energy physics. A year later, he began as a researcher at Caltech and has been part of that institution ever since. In the 1990s, Dr. Barish and his team of researchers began working on the LIGO, Laser Interferometer Gravitational Wave Observatory project. For about a decade, the team was searching for evidence of gravitational waves, and but could not find any until they added a lot more sensors and capability, which in 2015, after a lot of work and upgrading of the detectors, the team finally discovered gravitational waves. Gravitational waves are disturbances in the curvature of space-time. Think of a large celestial object, such as a star, sitting on a net, and the net is curved. This discovery led the team, including Dr. Barish, to receive the Nobel Prize in Physics in 2017. Dr. Barish joined UC Riverside as a faculty member in 2018 in the Department of Physics and Astronomy, and he teaches a graduate seminar for UCR students. please join me in welcoming as our speaker this morning, Dr. Barish, our Nobel laureate. Dr. Barish.
Dr. Barish, your microphone is muted.
Trying to keep it quiet. Thank you. Thank you, Gordon, for the very kind introduction. I'm very happy to be here. I think this activity in the summer is unbelievable. The number of students that participate and the student programs that give young students some sense of the most exciting things that can be done to help our society using scientific and engineering tools. I'm going to give a little talk to give you some sense of something that may be a little less practical but important, and that's why what I do in physics by talking about my work. I need to share my screen, and I'll give you just a little bit of a talk. Does my screen show? Okay, so I assume everybody can see my screen now. And so what I'm going to do is talk about research that maybe isn't driven by really important practical problems that we've been dealing with in this summer study, summer research, especially the student ones, where we worked on problems like smart cities, where we can learn how to handle transportation in a more effective way, or microgrids that will enable us to use renewable energy and attach it to the larger grids. Our artificial intelligence with all its different ways of helping us solve problems and do them more effectively. I'm going to talk instead about research which is performed in a very similar way. I was started as an engineering student, which Gordon didn't mention. And my heart is very much in the same techniques as engineering, and I'll show you just a little bit of that. But the research itself is driven purely by curiosity. In other words, rather than, maybe it sounds like a luxury, but I'm going to try to convince you that it's not. And also it's very important in itself. So I'm going to talk a little bit about curiosity and a little bit about my research. Of course, the little cat here is curious. But we learn from a young age that curiosity is really not a very good thing. We have a rather well-known saying, curiosity killed the cat. You can see these two pictures here of cats getting themselves into a little trouble because of their curiosity. And that attitude pervades society, I believe, in a rather negative way, especially in teaching. And so let me say a few more words just about curiosity. You can pick up cartoons anywhere and see that a cat gets in trouble because of curiosity. What happened to him? One dog says, I don't know. He just came up and started asking a bunch of questions. Okay? And the cat gets in trouble. Maybe closer to research, you can see in this one that the cats are laying on the ground because they basically were doing something like I do, or even you do in engineering, which is scribbling and lab work and so forth. And this is common. I didn't have to work very hard. It affects our education. And you can see by this cartoon that the attitude is one that a good teacher really has to buck. If you finish your first year of teaching and you haven't destroyed the innate curiosity of your young students, you are a successful teacher. And I think all of us, as we're close to being adults, know that we're not the same. Most of us are not the same as we were when we were 5 or 7 years old, when we were pests, because we asked so many questions. Young kids ask a lot of questions. Then we send them to school. We teach them a lot of things, but somehow we typically beat the curiosity out of them. And this just isn't a good thing, whether they end up being doing what I do, but even in life. So a lack of curiosity gives us a society that I claim is really deficient. So the society we live in typically has people that spend a lot of time watching television, but have very little idea how a television works and how it gets the picture that they're looking at. They then go in the kitchen and use a microwave and have absolutely no idea how the microwave happened to cook the food that they're eating. Or they spend too much time on a cell phone and have no idea how it tells them where they are and how to communicate with each other or ask questions through Google or whatever they do with it. Or even as mundane travel and get on an airplane but have no idea what makes an airplane fly. How we can have a society where we live in our everyday life and almost everything around us, most people don't understand, seems to me to be a great deficiency. I'm not going to tackle that problem, instead say that somehow, by some miracle, I escaped this problem of having curiosity totally beaten out of me. So when I was a student in engineering in Berkeley, I got intrigued by physics and transferred into physics because the goal of physics is just to understand nature, how it works. And in some sense, most of what we choose to do is where we jointly have curiosity. So the research I'm doing on gravitational waves fits that totally. I'm going to give you just a little picture of that and what drove it and what just a touch of the technique that's involved. We all learned, any of us in school, what gravity is. In fact, it was taught to us by Newton, and he was perhaps arguably the greatest physicist of all time. He wrote a book in 1687 called the Principia, and in that book, he wrote a theory of gravity. He also wrote down the scientific method in that book. But in that book, he taught us that there's a gravitational pull that pulls two masses together. It goes inversely like the square of the distance that they're separated and the product of their masses. And there's some proportionality constant that tells you the strength of it. That actually took 100 years later when it was determined what that is. And he made the rash statement that this law was universal. And indeed it is. You use the same formula, whether you're talking about the apple falling out of the tree, the moon going around the earth around the sun, or even something a little more subtle like the tides. All of that uses this, and he put it forward in 1687. And by the last century, essentially no one had found almost anything wrong with it. I'll show you the only thing that existed. Then Einstein came along. And I've written a little formula here. I'm not going to explain it. I'm just using it for completeness. It's a little harder. And he did not make a new theory of gravity that throws away Newton's theory. The way physics advances, science advances, is to learn something that maybe replaces it because it's more powerful. Newton's theory is perfectly good for all that Newton did, but it is deficient. And Einstein's theory, which is somewhat different, helps with those deficiencies. So why did we need a new theory of gravity? Well, first there was one little problem. This is not what motivated Einstein. The only problem that existed in the early 1900s, more than 200 years after Newton, that wasn't totally described perfectly by Newton's theory, is the orbit of our planet that's closest to the sun, Mercury, around the sun. Every time it goes around the sun, it gets pulled by the locations of all the planets and moons and so forth in our solar system. And it comes back to a somewhat different place, like a daisy pattern, like you see in the cartoon drawn here. You can calculate completely and accurately with Newton's theory where it should come back, but you don't quite get the right answer. It's about 10% off. So that was what existed when Einstein came. In fact, most people at that time felt the difference was probably due to the fact that we hadn't discovered everything in our solar system, and perhaps there was a planet missing between Mercury and the sun. People even gave the planet a name. They called it Vulcan, which was reinvented for a television program. But this was a planet that was even looked for by NASA in the 1950s and 60s and 70s. So anyway, this problem Einstein solves in his theory. but that's not a major accomplishment because it could have been something else. So what does Einstein do? The first thing is all of us were kids, and when our teacher told us, which happened to many of us, that when you jump up, the earth pulls you down, we accepted that. But not very many of us asked the teacher why the earth pulls us down. Newton didn't tell us that. He gave us a formula, but there's nothing that explains why the earth pulls us down. Einstein explained that. And it's got to do with his formula being an integration of space and time together that warps space and time, as Gordon mentioned it in the introduction. And you can think of it like a trampoline. If you put the earth on a trampoline, it makes an indenture. And then if you take the moon and put it around it, of course, it's attracted to the earth. But if it's moving, it goes around the earth. And similarly, if the apple is in a tree just above the earth, it gets attracted because of the shape like a trampoline. Or you put a marble on a trampoline, when there's a bowling ball in the middle, it'll be attracted to the bowling ball. And so this curvature, distortion of space-time that always seems so exotic in Einstein's formula and what's said about Einstein, warpage of space-time, is all very important in explaining a very simple concept, why gravity pulls something toward it. The second is a little more interesting, I think, than the first one. The second problem that existed with Newton's theory, and this is one that Newton recognized if you actually read the Principia in detail. He recognized this problem but had no idea how to solve it, but he noted it. And that is something we call instantaneous action at a distance. That sounds very fancy, but what it means is when the apple falls, you know about it immediately in Newton's theory. That's okay, that didn't affect anything. But imagine that the sun disappeared right now. It would take 8 minutes for us to know that because it takes 8 minutes for the light to get from the sun to us. Likewise, in Newton's theory, you would have known it immediately, which is illogical. In Einstein's theory, gravity travels at the same speed as light. And so it would also take 8 minutes to get to us. So he solved these two conceptual problems. That is, how do you explain why the apple falls and instantaneous action at a distance? That doesn't make you accept a new theory. Those are just explanations. He made one and then a second prediction of something that would be new. The one that made him famous in the world is the bending of light. If we go through this curvature of space and time, light's going to follow the curvature of space and time so that it doesn't necessarily go what we all think in a just straight line. So he actually proposed how you could test that. And that is, imagine light that's coming from behind the sun, grazes the sun, comes near the gravitational field of the sun, it should get bent. And so he proposed that one should look at stars going behind the sun. And as the sun, it goes through a full eclipse where you can actually see a star that's behind the sun or near the sun as it goes behind the sun, then you could measure this curvature that would happen because of the mass of the sun bending the space right around it. And in fact, he calculated how much it would bend. And Sir Arthur Eddington, who was Arthur Eddington at that time, he became Sir Arthur Eddington by this measurement, went to the Southern Hemisphere in an expedition of physicists, and they measured this and proved Einstein was correct. And this is actually what made Einstein a household name. It made all the newspapers. The bending of light, of course, seems so ridiculous that the New York Times wrote this article, which I'm not going to read, but if you read it, it's how ridiculous it is that physicists are talking about light bending and so forth. And that was what made people believe that general relativity was probably right. It explained all the unexplained questions that I said and predicted something new, which turned out to be true. It predicted one second thing, and that was gravitational waves. That was in 1916. Einstein noticed that if he looked at the equations of general relativity, they looked very similar to the equations of electricity and magnetism. Electricity and magnetism, we know, makes waves. We have light and radio, microwaves, as I mentioned, for a microwave, that's all electromagnetism. So the fact that electromagnetism makes waves, Einstein not developing from the theory that gravity should have waves, but by his genius making the extrapolation that since it looked a lot like electricity and magnetism, there must be waves there as well. So he wrote a paper in 1916 proposing that gravity would also have waves. It took another 50 years before people could actually develop the equations of those waves from the theory of general relativity. It was not easy. And then it took another 50 years for us to detect the gravitational waves. So the waves come about from something like, think about any sort of planet going around the Earth or anything that goes around each other, like I've shown here, and the waves go out from that. In our case, the two objects were two objects that are in exotic objects that we look at in the universe called black holes that were going around each other. As they go around each other, they emit waves. And those waves we detect by the distortion of space and time when it gets to the Earth. Now is my little technical part, which I inserted, which is what do you have to do to detect them? You have to detect a distortion of space and time. So that means that a distance in my picture here, vertical compared to horizontal, won't be exactly equal anymore. It'll change at with the frequency of the light, actually, of the gravitational wave that's coming. The only problem is that distortion is incredibly small. That's a problem for me as a physicist. It's pretty good for us as people and living in this universe because the distortions are small enough so that most of what we do isn't disturbed by it. They're not small because gravity is weak. They're small because space itself, in some sense, is like a material that's very stiff. And so it's hard to distort it very much. In fact, the numbers are so small that I give them here. We use a technique called interferometry that measures the difference between the distance vertically and horizontally here by splitting a light beam from a laser, sending it in both directions. They hit a mirror, they come back. You invert one with respect to the other. If the distances are equal, they would cancel and our sensor would see nothing. But if one gets a little longer than the other or shorter than the other, we would detect that. It varies back and forth between the vertical and horizontal because waves go up and down. And so it changes which way, kind of like the picture I've drawn here, a couple cycles a second. The accuracy and the challenge in the experiment that we did and why it was so hard is that we have to be able to see a difference in these two lengths by 1 part in 10 to the 12th, that's a pretty small number, of the wavelength of the light we're using in the laser beam. Secondly, it turns out trying to measure these very, very tiny numbers, the Earth shakes too much. So we also have to isolate this detector from the Earth itself to, again, 1 part in 10 to the 12th. And those were the challenges that took us more than 20 years to solve. This is a picture of the detectors we have. One of them is in Livingston, Louisiana. The other's in Hanford, Washington. The two institutions that did this were Caltech and MIT. We proposed to have one of them in the Owens Valley, not so far from Riverside, and one near in southern Maine. The politicians approved and funded us, so we're happy, but they decided to put in states that the senators who supported it the most liked. And so we have one in Louisiana and one in the state of Washington. They're separated by 3,000 kilometers. At the speed of light, that's 10 milliseconds. I'm just going to show one technical thing just to show that it is technical. This is the object that enables us to isolate the detector by a factor of 10 to the 12th from the Earth. It's a whole complicated thing here that's shown with springs and so forth. So what is it? It's basically uses two techniques. First, how do we get rid of the shaking of the earth in everyday life? The place we know it the most, and we just borrowed that idea, is in our cars. We drive down the car and there's shock absorbers. So what do the shock absorbers do? We go over a bump. You can't get rid of the energy. It just transfers it to a much lower frequency. And the bump feels very smooth and we're comfortable in our driver's seat or passenger seat in the car. So we do the same thing. We just made very, very fancy shock absorbers like are in the cars with just the right squishiness. And instead of being like a car, we had 4 layers of it. So what doesn't get canceled by the first would get canceled by the second or the third or the fourth. And altogether, that gave us a factor of 10 to the 10th reduction. That's a lot of reduction in the shaking of the earth. But you remember the number I put was 10 to the 12th. To get the last factor of 100, which enabled us to make this measurement, we had to do something else. So again, we just stole a simple idea and applied it to a different application. And that is something which many of us experience. We got on an airplane, the noise of the engines roaring bothers us. So we invest in Bose or somebody's nice little earphones that we put on our ears, and the noise magically disappears from the engines, and the stewardess still can talk to us and ask us coffee, tea, or milk. What that does is measure the ambient background from the engines and cancels it. And the stewardess talking to us isn't ambient, so we still hear her. So we want to do the same idea. Of course, we have nothing to do with acoustics. We're doing motion. So what we need is seismometers. So we put seismometers inside this array of shock absorbers, and the seismometers themselves sense any residual direction, motion and their direction, and we put little actuators and push back against it. And that technique, which was hard to develop because it's all three-dimensional, took us quite a while to develop, but it gave us the last factor and enabled us to discover gravitational waves, which I'll describe next. And I'll point out, we make the most stable table in the world by this technique. So people are looking at using our ability to do this to make more stable tables for example, microelectronics. This is the discovery. I'm going to end in just a minute. This is the discovery of gravitational waves. On the left is this was on the first page of the New York Times. It's raw data. It's 0.2 of a second, the evolution of a signal where the scale on the vertical is 10 to the minus 21 seconds. The top 2 traces are from the 2 detectors, one in Livingston, Louisiana, one in Hanford, Washington. And you'll see they spike, they wiggle back and forth, getting bigger and narrower, just what we expect. If you put one on top of the other, they fit each other if we slide one by 6.7 milliseconds, which is within the speed of light between the 2 detectors. If we compare that with Einstein, for 2 black holes colliding, we get this, I drew it again on the top of the picture here, the 2 detectors. The second is Einstein's calculation for 2 black holes colliding, and it looks just like it. And a simple way to test that is just subtract Einstein's curves from the measurement, and you just get the residual, no patterns, just a residual shaking, which is the noise and the residual noise in our instrument. So that's the end. They gave me a prize, and this is a picture at the Nobel and so forth. And life continues. So life after the Nobel, I'll just give you a quick sense. Curiosity itself, I emphasize, is a really special quality that I've nurtured, and I think we should all nurture, whether you do something as exotic as I did or not. I'm going to show you one more thing, which is beyond the Nobel and something we did more recently, and shows you maybe just an inkling of the value of doing the values other than developing maybe technology, which it shows you that can come from doing fundamental science that isn't even that particular science. So afterwards, we've detected an object that wasn't black holes. It was what are called neutron stars. neutron stars, in contrast to black holes, give off electromagnetic radiation. So it turns out that it was seen in an object that gave electromagnetic radiation on a satellite called the Fermi satellite at 2 seconds after we did. That meant that we detected something with gravitational waves that also was detected with electromagnetic waves. The fact that it was seen by this satellite, we then alerted the whole astronomical community. Astronomers have a way to do that. And there's something like 2,000 instruments around the world that are noted, not amateur. And more than 1,000 of those turned and looked at this place in the sky. They varied from looking at the visible, infrared, radio waves, even neutrinos. And when they did that at different times, they saw signals. So this was all recorded. That data gave a spectrum of how much there was at different wavelengths and so forth. And that fit a picture called a kilonova picture. I'm not going to go through that at all, but point out that it answers possibly something that's been a big puzzle. Physicists think they're supposed to describe everything in nature that's there, so we make up explanations even if they're not right or quite right. And one puzzle we've had that seems rather something we should know is, how did the heavy elements get into the earth? How did we get gold and platinum that we go and dig for in the earth that we live on? How did they get there? Turns out that the universe is made out of mostly hydrogen and helium, so that's not heavy elements. The main way we make matter that gets into something like planets are believed to be from the fact that stars, which are a burning nuclear fusion process, is the burning of nuclear matter, starting with hydrogen, then helium, then lithium and carbon and so forth, through the fusion process. And so that makes all the elements, including iron, but no higher than iron. Fusion doesn't make elements as heavy as gold or platinum. So most of what we have in the earth is probably made from stars having burned up their fuel, made into a supernova. Their matter went out into space and made the earth, but that doesn't explain gold and platinum. So when we look at the periodic table, it turns out that everything after gold and platinum is something we know exists because we make them in the lab. And somebody makes them in the lab, they discover it, it's a name, and it goes up to very, very heavy elements. But what about nature? How did the ones exist in nature that we find? And the ones beyond iron, we didn't have an explanation for. However, if we look at how they're made in our laboratories, they're made generally by somebody going into a laboratory, taking a beam of neutrons, running it into some heavy element and making a heavier one, and then becoming famous by naming it and making a discovery and getting it onto the periodic table. The collision that we saw is a collision of two neutron stars, which seems like the same kind of process that people use in the labs. And it is. So I can go calculate now in this neutron star process, which was what we cared about, just seeing the process, understanding neutron stars, how much gold or platinum it'll make by using the model that we have, that it's this neutron star collision. It may be right, it may not, we've only seen one, but it turns out the one that we saw last year, there was a collision of two neutron stars, by our calculation, made 100 Earth masses of gold. So in the past, that of course didn't get into our Earth, but in the past there were previous ones that made the gold, platinum, and so forth that we find in our Earth. So we may be right, we may not, but this is probably now the best explanation we have for how the heavy elements got into the Earth. With that, I'll basically leave you with my food for thought and congratulate everyone. I'm happy to have been part of this and for running such a nice summer program. Thank you.
Thank you very much, Dr. Barish, for sharing your words and your keynote with our students and program. We really appreciate your involvement and your dedication to education.
I'll stop sharing screen, sorry.
Oh, yes. At this time, we'll transition over to introducing our module leaders. We'll begin with Dr. Matt Barth, who is the Director of CSERT and a Professor of Electrical and Computer Engineering at UC Riverside. He was also the module leader for our Smart Grids and Transportation module. So, Dr. Barth.
Great, thank you very much, Elliot. As director of CSERT, just wanted to mention that CSERT's very proud to be part of the STEPCon process. We've been working in this STEP conference for a number of years, working closely with Gordon Bourns and everyone else, and we're very proud to be part of this. In terms of my module, I focused in on sustainable transportation. Part of what we do out at CSERT is focused on transportation. And in fact, CSERT itself is part of a larger National Center for Sustainable Transportation, which is a U.S. Department of Transportation National Center that we share with a few other universities that we do research with. So the module that we focused on was sustainable transportation. I think everyone's aware of all the problems that come about with our transportation system, particularly here in Southern California. We have a lot of vehicles on the road. We have a lot of congestion. There's air quality problems. We burn a lot of fuel. And so really, we're trying to figure out how to solve this problem, particularly with issues of air pollutants as well as greenhouse gas emissions, which is a very important issue we need to focus on. So in general, we usually say there's 4 things we can do to improve our transportation scenario. One is improve on the vehicles, and of course we're doing that by trying to electrify everything. So we have rules in place here in California that will electrify the vehicles hopefully in the 2030s and 2040s. We're focused on improving the nature of the fuels, and if we again rely on electricity, we can make that very cleanly and very renewably. We also want to see what we can do about reducing the total number of miles that we travel. We have a lot of commuters that go, for example, between Inland Empire and our major cities, and so that chalks up a lot of miles, which again in itself is a problem. But really what we focus on here at CSERT is 2 issues. One is automation. How does automation improve problems? And the other one is connectivity. How can vehicles talk to each other in order to improve the situation? So our module really focused in on the pros and cons of automation, how we do it. And as an electrical engineer, we often look at control systems. We look at communication systems. And in particular, in control, we really look at how we can control the longitudinal motion, meaning, if you're a driver, you can hit the accelerator, you can hit the brake pedal. But if you were to automate that, how can you do it in a way that it's smooth, that it smooths out the traffic flow, and as a result, that minimizes the total amount of emissions that become, or it minimizes the amount of energy that you would use. So we had a module with an actual traffic simulator where the students could actually play around with things such as the longitudinal control, how cars follow each other. And there's a lot of parameters you can set there. And I think the students had a chance to play around with those parameters and see what the overall effect was on I'd like to recognize and introduce our newest faculty member in electrical and computer engineering. So Dr. Basak Guler came to us, and she does quite a bit of work in signal processing and artificial intelligence. So Basak, you want to give your learning module?
Yes, thanks for the introduction. So I'm an assistant professor in the Department of Electrical and Computer Engineering at UC Riverside. So I'll give you a brief overview of our training module and what were the goals and what we wanted to achieve. So I'm going to share my screen. Okay, so can you see my screen? I hope it works. Okay, so machine learning, as we said, machine learning and AI is allows us to train mathematical models. So it allows us to train a model that can learn from experience. As it sees more and more examples, it can learn to make inferences about the examples that it hasn't seen before. For example, as an example, you can think of a autonomous vehicle or a self-driving car that needs to navigate without a driver. And for this, it often uses the sensors from sensor information that it gathers from its environment, such as from radars or lidars, and it needs to interpret these sensor information. And for this, we often use machine learning techniques to decide what decision to make decisions about the real world. So as I mentioned, we focused on a specific branch of AI, which is machine learning, and it has a large number of real-world applications ranging from image recognition to speech recognition, as well as product content recommendations or navigation, even gaming and computer security, fraud, and malware detection. So in this module, we have first looked into the basic principles of machine learning, and we basically trained a simple machine learning model for image classification. Okay. For this, we used the Python programming language, and we used a browser-based service that allows us to run our code, our program on the on a web browser. And then we introduced how to do machine learning, how to use the training data set and the test data set, how to train a model, and then how to test our model, the accuracy of our model for an image classification example. And all of these techniques, all of these programs and data sets were available, publicly available. So the students, if they're interested, can continue to work on this in their own time. And then at the end, we have discussed some limitations of machine learning, of current machine learning systems. For example, the first one was bias and fairness. This is a big and active area of research right now. All right, I'm going to just quickly go to this. Yep, limitations of machine learning. For example, we have seen that in our learning module that the machine learning, the quality of our model that we train in by using machine learning highly depends on the quality of the training data set. So if the quality of our training data set is not good, then we will have some problems in our trained models. One of them is bias. For example, if our data set does not represent all of the, for instance, the population properly. For example, you can think of a machine learning based tool to automate job application reviews. And if there are some users that are, there are some samples that are underrepresented, and then machine learning models usually bias against those underrepresented samples and then tends to favor the more represented samples. And so we need to make sure that our data sets are fair against all of the examples that we have showed to the machine learning algorithm. Another limitation of machine learning was adversarial attacks. We have seen that in this training module, it is possible to create adversarial inputs to a machine learning system that cannot be detected by a human eye, but it can fool the machine learning system to make wrong decisions. And this is also, this can be a very big challenge. For instance, if you have an autonomous vehicle system or like a smart vehicle or a self-driving car that needs to make decisions based on the information that it gathers from a camera, for instance, if these images are a little bit distorted, if there's a little bit of noise added to these images, then the, this vehicle can, for instance, interpret a stop sign. Instead of a stop sign, it can interpret it as a speed limit sign, and it can cause major problems in transportation networks. So I think this concludes our training module, and it was a very nice experience for me, and I hope also the students have liked it. Thank you.
Thank you, Dr. Guler, for sharing your module and an overview of what the students had a chance to learn. We'll continue on to our microgrids module, and to present on those is Dr. Sadrul Ula, and he is a research faculty at the Center for Environmental Research and Technology. Dr. Ula?
Thank you. Yeah, my area of expertise is renewable energy integration with sustainable other energy sources. And the module we work with the students where these different integration of systems which makes it more sustainable. And one of the solution is microgrid, which is an independent mini system using renewable sources and energy storage. The basic challenge we have in using electricity, which is electricity, as you know, is essential in running all the, whether it's transportation, traffic lights, or computers, cell phone, laptops, all used to come from fossil energy, to some extent from nuclear energy also, with serious impact on environment. So California and other states have moved towards cleaner energy, which is basically solar energy or wind energy. And there are certain future fusion and other hydrogen-oriented energy has good potential. But these sustainable energy sources are intermittent in nature. So it's not there all the time. And say, for example, solar is a good example, very successful in California, but it's not available when sun is not there at night. We need energy storage to capture surplus renewable energy during the daytime and then make it available at other times. One of the challenges California is facing is non-availability of renewable sources in the evening hours when sun is not there. And as a result, in August, there were some rotating blackouts to have the system survive this demand in hot heat wave when solar energy is gone towards the evening. In August, we had this. And then even this past week, we had what they call public safety power shutoff, PSPS, when strong wind creates the distribution and transmission lines hanging wires touch each other and create spark and create fire in many vegetation areas. So as a precautionary measure, they have to shut off power for some time. Now this creates serious problem in critical infrastructure like hospitals and fire stations and of course regular homes and so on. Our solution is microgrid, which is that the grid connection is not essential. Locally generated solar energy with battery energy storage can help solve this problem. And at CSER, at UCR, we have microgrids in our facilities with essentially 3 microgrids supplying 3 different buildings with battery energy storage and solar PV and building controller. And the module allowed students to play with this microgrid and add more solar or more battery depending on the design issues and the challenges. And one of the related challenges is how to bring and distribute power using the distribution line, transmission line. And we provided a software where they could simulate these different scenarios and see overloaded lines and where to place future renewable energy sources and how to bring it to the users in a reliable fashion, independent of weather condition and high demand, by using all these modern advanced controllers and various energy sources and lead us towards sustainable future with cleaner energy and satisfy California's future mandate, including transportation, cleaner transportation, as Dr. Barth mentioned, that also is electricity oriented. So students had an opportunity to simulate different scenarios and offer their suggested solutions on which location to put all these different energy sources. Thank you, that's all.
Thank you, Dr. Ula, for providing an overview of the microgrids module. And now to share a few words on our Clean Airs Sensors module, please welcome Nicole Cleary, who is the Deputy Director of CSERT.
Hey, thank you, Elliot. So good to be here today. I'll be talking about a summary of the clean air sensors that we made in our learning module. Let me share a picture of those. Can everyone see that? Okay, great. So this is a picture of the particulate monitor sensor. And the reason why I chose to build this for our learning module was essentially, I wanted the students to have some hands-on learning experience, something they could build and not necessarily just type on the computer all day, although there was some coding involved. And the reason why we chose particulate matter is because this is an important pollutant in the Inland Empire today for two reasons. First, when we think about wildfires that's going on, you can kind of picture, yes, if you can see the smoke, you're being impacted by the fires. But if you can't see the smoke, there's another way you can tell, and that's by using these PM monitors. And so we encourage the students to use this and put it outside to see if they could see any signal from the wildfires that were occurring. You can also visit the EPA website and then compare. They have some similar sensors, and the students could compare that to what the sensors in their hands said. And the second reason why we chose particulate monitor is because right now there's a lot of logistics and warehouse growth in this region. And one of the predominant emission sources is from these heavy duty diesel trucks operating, and they emit particulate matter. And so we really wanted the students to, maybe if they lived near a warehouse or a heavily traveled road, see if they saw higher particulate in people that lived in maybe a more rural area. So that was kind of our project. I think I have one more picture. Show operational. There it is, operational. So, and then what I hope the students took away from this was, first of all, understand a little bit about air quality. So you might look outside, it looks like a great, nice sky, blue day, but there's some unseen things that might be impacting our health. And the way you measure these is through sensors, such as what we built in the module. The second thing I hope the students took away from this was understanding how their behavior could actually impact the environment around them. So one of the lessons that we did after the sensor was built is walk around the house with your sensor and see if you can increase the particulate loading in your home by vacuuming or perhaps cooking. And then once they say, wow, the pollution's really high in the house from mom cooking, then they can see, okay, how can we lower that pollution? Can you turn on the fan or a vent and lower your particulate burden? And then finally, I hope the students took away the fact that science isn't perfect. And so when you look at some of the results coming out of this and some of the sensors didn't make sense, that is a part of it. And you need to understand there's quality assurance, there's quality data that you need to go through and look at. And so we didn't get to that in this module, but I'm hoping students will tune in. We'll expect to do more modules where we can get into those kind of questions. And at the end, I hope there's a lot of students out there that can be advocates and show the community and their parents about how you can read low-cost sensors information and make decisions about those information. And then finally, before I wrap up, I did want to share another opportunity. Let's see. Give me 1 second. And Jill will be, oh, sorry. Okay, here it is. So Jill will be putting in the show notes the information about this short film contest that you'll see here. And this is open to all the community, the teachers, the students, whoever wants to create a little short video about how they think air quality is being impacted in their area. This contest is open through the end of this calendar year, and we will feature the winning video on our website and in our conferences, and there is a nice little cash prize. So please visit our website for more information on this, or see the link in the Zoom chat. Thanks everyone, thanks Elliot.
Thank you, Nicole, and thank you to all of our module leaders and Dr. Barish for their presentations today. Our last presenter is Dr. Damien Octeau, who is a staff software engineer at Google, where he leads the detection of potentially harmful Android applications with artificial intelligence. He received his BS and master's degrees from École Centrale de Lyon, France in 2007 and 2010 respectively, and his MS and PhD degrees in computer science and engineering from the Pennsylvania State University in 2010 and 2014 respectively. He was a research associate with a joint appointment at the Department of Computer Sciences of the University of Wisconsin-Madison and at the Department of Computer Science and Engineering at the Pennsylvania State University. Please join me in welcoming Dr. Damien Octeau.
Thank you very much for the introduction. Are you able to see my screen?
Yes.
Perfect. Thank you. So it's a great pleasure to be here today speaking at STEPCon. So as you mentioned, I lead the detection of potentially harmful applications with machine learning. And so to kind of talk a little bit about, before I talk about some details about that, basically if you have an Android device, the visible part of what I do is actually on your end as the user through Google Play Protect. So what that is a suite of security protections for Android and for Google Play for everyone who actually has Google Play. So for those of you who don't have an Android device, Google Play is basically the main store that is distributing Android apps. And so what this does essentially is it looks for and removes potentially harmful applications from the Google Play Store as well as from devices themselves. By potentially harmful applications, we mean things like, for example, ransomware and so on. These are all the kinds of threats that we look for. And what you need to to kind of remember in summary is that these applications can basically do pretty bad stuff to you, including stealing money from you, or doing things like stealing your data, and that is something that we protect you against. We do this through a couple of key technologies. The first one is an application scanner. So this is something that I basically primarily work on. It's integrated with Google Play, and this kind of happens, if you think about it, it's kind of in the cloud, in the background. It's not something that you see as a user, but that application scanner, which looks for potentially harmful applications, or PHA for short, is coupled with some on-device protection. So it's this Google Play Protect app that is pictured on the the graphic on the right side. And that will run on your device and scan applications both at installation time and also at regular intervals. And it will basically query our systems and try to figure out whether you have on your device any of the known potentially harmful applications. Just to give you a few key figures for the scale at which we're operating. So we have an installation base. So it means the number of people or the number of devices that we protect. That's over 2 billion. We have we are scanning daily, actually a pretty large number of applications. It's over 50 billion applications, and that's across all the devices. Basically all the applications across all the devices that we protect. Back in 2017, we stopped over 1.6 billion PHA installation attempts. So these numbers, are from a couple of years ago. You can imagine that our footprint is probably larger now, but even if these numbers are a couple of years old, I think it gives you a pretty good idea of the scale at which we're operating. So when we find something, how do we enforce? So how do we protect people in practice? So if it's an application that's in the Google Play Store, since we control the store, first we try to prevent PHA from entering the store in the first place. If something does get through, we will remove it from the store as soon as it is found. We also have the ability to protect users that install applications, even from outside the Play Store. And what we do there is that we will check applications when they are being installed, and we will also scan the entire device at regular intervals. And if we do find something, what we will do is we will either warn the user, or we will, we can outright completely remove the application, depending on the severity of the PHA. So I work in 2 areas of work. So the first one is cybersecurity, or security for short. And this area is about protecting people, as Dr. Guler said in an earlier learning module. We're really trying to make the whole environment more secure, your computing environment. I like this area because it's a very broad area. There's hardware security, network security, including security of the internet, operating system security, software security, and so on. I myself work in software security, and because it's such a broad area, it's really hard not to find something that you like. These are all pretty distinct but related areas, and I think it's easy to find an area of cybersecurity that you might be interested in. One more reason why I like security is because I think it's a great way to learn about computing. In order to be able to secure a system, you actually have to learn how it works, and you have to know how it works very well to know what all of the avenues are for potential abuse. The second area that I work in is artificial intelligence, and more specifically machine learning. Basically, the idea, as was explained earlier, is to have the computer learn concepts automatically. So what we do in practice is that we feed our learning system a number of examples of potentially harmful applications. We also feed examples of harmless applications, and the system will automatically train, learn, and generate a model. Now, once we have this model, when we see a new application for which we don't know if it's harmful or harmless, we will apply the model to it, and the model will automatically tell us whether it thinks that the application is potentially harmful or not. This area of machine learning has been a game changer in many areas, enabling things like self-driving cars and so on. In our area, it's actually been no exception. It's really made a very huge difference. You've seen, a few slides ago, the scale at which we operate with billions of users, millions of applications that we need to kind of sift through to find the very few potentially harmful applications among a mass of millions of applications. This has made a really huge difference in terms of like finding the needle in the haystack. So yeah, these are the two main areas. I think this is very much related to at least one of the learning modules. If we take a step back, since you might be curious about what it's like to work at Google, and you might be making decisions about your future in the coming years. So there are a few reasons why I actually enjoy working at Google myself. The first one is the impact. So we literally are protecting billions of users from potentially harmful applications. And I think it's something that you can feel good about when you have that impact on such a large population of users. The second thing that I enjoy is that the work is actually very challenging in a good way. Technically it's challenging. We're really I don't think there's anyone else that has solved this problem at this scale, and so we're kind of writing the book as we go. There are also some other non-technical aspects. It's a pretty difficult endeavor, and there's my team is doing, for example, detection with machine learning. But there are many other teams, at Google that also work in the same area, and we have to, for example, make sure that our work is used properly, and so on. And there are some non-technical challenges as well, and I think these are all good things. The last thing that I enjoy about Google is that I have, I think, very smart colleagues. There's this saying that says, if you're always the smartest person in the room, you're probably in the wrong room. Well, I don't have that problem at Google, and I think that's a great way to grow and to challenge myself. How did I get there? You might be wondering, what's a good way that you get to Google? So on my side, I have a relatively atypical profile. I was educated mostly in France, as you probably have guessed from the accent, and this is pretty atypical. I would say that most of my colleagues go to Google after doing a bachelor's degree with a major in computer science. That's, I would say, most of the the engineers at Google. It doesn't mean that there are not some atypical profiles like mine. Of course, people of all types of profiles are welcome if they can do the job. But I think most people just do a CS undergrad essentially. Now, finally, I often talk to undergrads or graduate students who have a few, I think, misconceptions and don't even think about applying to Google or other tech companies just because they think they don't have a chance. So in a way, they kind of self-censor for no good reason. And even though it's still a bit early for you at your current level, I think I kind of want to plant this idea in your mind that it's not something that's out of reach, given the right conditions and the right education. And there are a few kind of preconceived ideas that I'd like to take the opportunity to dispel. The first one is, well, the Google interview is too hard. I think it's definitely not easy. The truth is it's not easy, but it's definitely fair and feasible if you have the right, first you have to have the right CS fundamentals, the computer science fundamentals, algorithms, coding, these are obvious ones. And you have to practice for interviews. And I'm putting those as two separate bullet points. I think the first one is one skill set. Taking interviews for tech jobs is a skill set by itself. So really practice for interviews with a friend and so on. The second preconceived idea that you might have is that, well, I have to start early. If I haven't, if I didn't start coding when I was 10 years old, it's too late for me. I have to, to be like an early CS genius or something like that. No, I'm a perfect counterexample of that. I took my first computer science course when I was in my third year of undergrad. I was not even a computer science major until I did my master's degree. So really, especially at your level right now, you still have plenty of time. It's not too late. And the last thing that I sometimes hear is that, well, I'm not good at it. Maybe I took a class at some point. It didn't go well. I just wasn't born talented in this. I would say, maybe you're not talented in it yet, but it doesn't mean that, that cannot change. And I encourage you to kind of look up maybe some videos on this concept of the growth mindset, which is, the idea that, what matters more than your, the skills that you have, the kind of some of the natural abilities or natural talent that you were born with, is how you actually approach learning and how do you approach failure. So when you fail at something, do you just give up? When someone gives you, constructive criticism, do you give up? Do you take it personally? Or do you take it as an opportunity to grow? And that is this idea of the growth mindset. Is that, like maybe you have a failure, but you kind of learn to go around, whatever obstacle you have, and little by little, you actually get better and better at something. Now, what you need in order to do that is to actually have something that you're passionate about, that you're curious about, that you think you want to spend time on, and so that you are able to grow skills in that particular area. Hopefully, it's computer science. If it really is computer science or something else, that doesn't matter. That's something that's personal. But you really have something that you're passionate about and that you're willing to fail and iterate and get better at. Also, obviously take advantage of opportunities. If you've participated in STEPCon, that's a great way to learn about all of these interesting applications. And don't forget to keep growing and keep an open mind. And with that, that's actually all I have. So thank you very much, and congratulations to everyone who took part in STEPCon and to the award recipients. Thank you.
Thank you, Dr. Octeau, for your words and encouragement to our students. We really appreciate you joining us today. All right, we're almost there. We're getting to the part that we're looking forward to, is the awards portion. Real quick, I just want to quickly recognize the STEPCon High School committee that put this on. Jill Barber, I don't know where she is. She's on this side of my screen, but Jill Barber, if you went on the website, if you saw any materials, basically if you saw anything STEPCon High School related, Jill was the person behind all of that. So I wanted to take a virtual bow at this point as one of our lead organizers. I also want to give credit to Nicole Cleary, who has been a champion of STEPCon for many, many years. And she's done a terrific job this year keeping us on track. So thank you, Nicole. We also had Angela Molesky of our marketing and communications team and Hannah Rolock of our marketing and communications team. Unfortunately, they weren't able to join for this meeting, but they served an important role and helped put together some of those wonderful videos that we had on the modules. All right, now we're at the very end. The awards recipients. All of our award recipients will receive a $100 gift card. We're going to make sure that it gets to the teacher because they're high school and they're underage. We can't share names, specific names, but the teachers are not kids, so we can share the teacher names. We'll start with our artificial intelligence and security module. The high school and the teacher that we're recognizing is Valley View High School and Janine Rue. She had 23 students take part in the ANI and security module, and we're going to make sure that one of their teams receives the gift card in recognition for their participation in our STEPCon High School. So congratulations, Valley View High School. All right, smart cities and transportation. Drum roll, virtual drum roll, goes to Valley View High School, but this is Camille Bates's class. She had 71 students take part in the Smart Cities and Transportation module, and we're going to make sure that they are recognized and receive their award. Because Microgrids is still working on their projects and there was more involved with that project, we're going to make sure that they receive their award. But because of that, we're going to recognize 2 teams with our Smart Cities and Transportation group. So we'll rewind momentarily and recognize Santiago High School's Vicky Liu's class, who had 70 students participate in the Smart Cities and Transportation module. So congratulations, Santiago High School, and to Vicky Liu's classes. In addition, we had several hundred students participate from all over California. This year was a special year for STEPCon High School, given the remote environment. we had the opportunity to engage with over 1,000 students who looked at the videos, engaged with this content, and it's a wonderful way for them to get exposure to these fields, these ideas, and just maybe a couple of them will be motivated, inspired to pursue the STEM fields in college and then go on to PhDs and careers in those STEM fields. So with that, we're concluded with our awards ceremony. Thank you all for joining us. Thank you to Dr. Barish. Thank you to Mr. Gordon Bourns for all of his tireless work. Thank you to Dr. Matt Barth, Dr. Sadrul Ula, Dr. Basak Guler, and to Nicole Cleary. And I'm missing one, three. No, I think I got them all. Okay, that's all. Thank you so much for joining us, and we look forward to seeing you next year at STEPCon 2021.
Thank you all. And Elliot, you did a great job organizing this and serving as our MC. Thank you.
Thank you, Elliot. You did, I agree. You did a fantastic job.
Good job, everyone.
Okay.
Bye-bye. Thank you.
Thank you.
Thank you.